So let's look at another example using the p-value approach. So last year, the mean composite ACT score for high school seniors was 21. Random sample of 100 seniors, that's going to be our N. Was taken, and that was taken this year, and the sample average composite score was 20.7. That's our sample average, so that's X bar. 20.7. Is there a reason to believe the national average has changed from last year? So we're just not doing a directional hypothesis, but a hypothesis of change. Population standard deviation 1.8. So sigma is 1.8. And then alpha 0.05. So we're testing against the 21 right there. So our null hypothesis is mu equal 21. Our alternative, since we're measuring just change from last year, mu not equal to 21. So that's step one. In step two, you normally would sketch rejection region. We'll sketch our p-value here. So, but first let's compute our test statistic. So our test statistic, x bar minus mu 0 over sigma divided by root n. So that's 20.7 minus 21 over 1.8 divided by square root of 100. That gives negative 1.67. So negative 1.67 would be about right here. That's our test statistic. So that's z-test. But since this is a two-tailed hypothesis, this is only half of the p-value. So that right there is actually p over 2, not p. Since this is a two-tailed test, p is the area past the test statistic on both sides. So if you had a positive one, that would be p over 2 over here. So then let's figure the area of that shaded region past the test statistic. So p over 2 is going to be the probability that z is less than negative 1.67. So we can do that again with normal CDF. So second variables, normal CDF. Our lower cutoff, negative infinity, so we could do negative 10,000. Upper cutoff, negative 1.67. Everything else the same. So 0.04745, so 0.0475. And that means then that p is going to be 2 times that. So we multiply by 2, so 0.0949. So if it's a one-tailed test, then your p-value is the area past the test statistic. If it's a two-tailed test, you have to double it. So then our test result here, well, our p-value now, which is 0.0949, is greater than 0.05, which is our alpha. So we do not reject. And so that means then our interpretation would be that there is not sufficient evidence. To conclude, the alternative hypothesis, to conclude the mean is not equal to 21. So instead, we conclude the mean is 21. So nothing's changed. So p greater than alpha, do not reject. P less than alpha, reject. Remember to double the probability when you're doing a two-tailed test. So let's see, that was step 1. Step 2, step 3 was our test statistic, and then computing the p-value. Step 4, determine what the result is, and step 5, interpret. And actually, I guess I forgot the state your alpha. So alpha was given to us as 0.05. So that was actually, which step was that? That was number 2 is select your alpha. So step 2 is actually right there. That would make this step 3, step 4, step 5, and step 6. There we go. So now it matches up with what we were doing before. And now if we go ahead and check this on the calculator, we can do that by going to the stat menu, tests, and that first one we're doing a z-test. We are using summary statistics here. Our mu0 we were testing against is 21. Our sigma was 1.8. Our x bar was 20.7. And then our sample size was 100. And then this is a not equal test. And we can come down here and we can either calculate or draw. If we calculate, you'll see there is our test statistic and there's our p-value, 0.09558. So that's differing just slightly from what we got here. This is 0.949, so this is off, in the last decimal place, and that's because of the rounding of our z-score. So now if you go back here and go to stat, tests, do the same thing, but then come down and instead of calculate, do draw. Then it sketches the distribution and it shows you the p-value. So 2 rejection regions, so this is p over 2, and there's our p-value, 0.956, to 4 decimal places.